Okay.
Okay.
Yeah.
All right. So I'm sorry. I want to do it this way. There we go. I think it's a little bit easier. Okay, so as I said, this is stoichiometry. It's the meat and potatoes of chemistry. So let's start by looking at the basic chemical reaction that a chemical reaction that you might look at. In this case, it's the combustion of methane. We can identify reactants. Reactants are always listed on the left side of the arrow. Products are listed on the right. So we have methane combines with oxygen to form carbon dioxide and water. These are your products. These are your reactants. Balanced chemical reactions they're balanced by the use of coefficients. In this case, the 2 in front of the oxygen and the 2 in front of the water. Those are known as the coefficients, and that's basically showing the relative numbers of each of the species in this reaction. So they represent the relative numbers of reactants and products and can be interpreted as ratios, 1 to 2 to 1 to 2, or 2 to 4 to 2 to 4, etc. So we can say that 1 molecule of methane reacts with 2 molecules of oxygen to form 1 molecule of carbon dioxide and 2 molecules of water. We could say that 3 molecules of methane react with 6 molecules of oxygen, etc. We could then scale it up. 1 dozen methane molecules react with 2 dozen oxygen molecules. The reality is that we don't ever work in quantities that small. They're much too small for us to deal with. We tend to work with moles. So we can scale it up to 1 mole of methane molecules reacts with 2 moles of oxygen to yield 1 mole of carbon dioxide and 2 moles of water. So the coefficients are just the relative ratio. I will say that while we can look at the ratios as 1 to 2 to 1 to 2, or 2 to 4 to 2 to 4, etc., we generally in the balanced equation use the lowest whole number ratio. So in a balanced equation, we have to have equal numbers of atoms of each element on both sides. Obviously, the elements are changing the molecules that they're residing in, they're reacting with other species, so they look different on both sides, but the number of each type of atom has to be equivalent, and that's to satisfy the law of conservation of matter. So if we have 1 carbon on this side of the equation, we need to have 1 carbon on the other side. If we have 4 atoms of hydrogen, we need to have 4 atoms of hydrogen on the other side. So that is simply to balance for the law of conservation of matter. So let's talk about some of the tricks that you can use to balance equations. And I will say that these are good balancing tricks. That you will always find a time when you have to do something different, that they don't necessarily work. But these are sort of the standards that you can start with in balancing chemical reactions. The first is balance 1 element at a time, and you do the atoms in compounds first. So if we notice there are 2 chlorines on the second product side and only 1 on the reactant side, so that tells us right off the bat we need to have at least a 2 in front of the HCl. That's going to balance the chlorine. That also gives us 2 hydrogens, and we have 2 hydrogens on the other side, so that's balanced. And then if we just put a 1 in front of each of these, we would have a balanced equation. Under normal circumstances, that 1 is assumed when you're asked to balance equations on a test or a quiz. I would recommend that you put those 1s in. It clearly shows that you understand that that 1 is there, and it's not that you just didn't finish balancing it. Another trick you can use is you can balance polyatomic ions as a group. So sulfate or nitrate, those can be done as a group. And if you look at this particular equation, you see that there are 2 nitrates on this side and 1 nitrate on the opposite side. So I can balance that by simply putting 2 in front of the sodium nitrate. That gives me 2 nitrates on both sides. That gives me 2 sodiums, however, so I need to put a 2 over here as well. When I do that, I have 2 chlorines, and I have 2 chlorines on this side as well, so that's already balanced. I have 1 lead on both sides, so the ratio in this is 2 to 1 to 1 to 2. A third trick that you can use is to focus on hydrogen and oxygen atoms at the end. Don't do them first. You'll get often make mistakes and go down the wrong path if you do that. Again, so I'm going to focus on the barium and the chlorine here. I have 1 chlorine on the reactant side, 2 on the product side, so I have to put a 2 over here. That's going to give me 2 hydrogens, and each of those hydrogens can react with a hydroxide. Let me use my laser pointer for a moment. This hydrogen can react with a hydroxide here to make 1 water. So with 2 of them, I can create 2 waters, 2 H's plus 2 OH's, and that leaves me with 1s in the other 2 blanks. Another problem that you might have is molecules that, or atoms, let me state that differently. Another problem you may have is when elements come in molecules instead of individual atoms. So this would be true for all of the diatomics, nitrogen, oxygen, hydrogen, things like that. But it also is true for things like sulfur. One of the common allotropes of sulfur is S8. So one of the things that you can do is to use fractions. Just make sure you clear it at the end. So if you notice, I have 2 aluminums in my product, so I'm going to have to put 2 aluminums on the reactant side. I then have 3 sulfur atoms in my product, so I need 3/8 of these sulfur molecules in order to form that product. And that would leave a 1 over here. But I need to clear the fraction. That is not finished that way. I clear it by multiplying through by 8. So this becomes 16 aluminum, 3 S8 molecules, and 8 Al2S3. And if you look at those numbers, you can see 16 to 3 to 8. You can't reduce that anymore. That would be the lowest whole number ratio. This often occurs, as I said, when you have other diatomics like oxygen. So for in combustion reactions, you're going to have the same issue. So if I look at, this is ethane. When I combust ethane, I have 2 carbons, so I need to form at least 2 carbon dioxides. I have 6 hydrogen atoms, which would be 3 water molecules. But now I have to balance the oxygen, and you'll notice that I have an odd number on this side. I have 4 plus 3 is 7, so I would need 7 halves of oxygen molecules. And so I need to clear that fraction by multiplying through by 2. So I'm going to, 2 times 1 is 2. This becomes 7. This becomes 4. And this becomes 6. And that would be the lowest whole number ratio. for that
Hey, Professor,
reaction. Yes.
can you explain again where you got like 7/2?
Because if you look at the product side, I have 2 times 2 or 4 oxygens contained in the carbon dioxides. I had 3 water molecules, each with 1 oxygen, so that would be 3. So 3 plus 4 is 7 oxygens. I have 7 oxygen atoms on the product side. I would need 7 oxygens on the reactant side. And so I can only get that by taking 7 halves of oxygen molecules. That's because oxygen comes in diatomic species. So if I took 7 whole oxygen molecules, I would have 14 oxygens. I only need 7. Does that clear that up?
Yes, thank you.
Okay.
And Professor, I'm sorry, can you just repeat what would be the common diatomic atoms where we would see that in?
Sure. You're going to see that in hydrogen, nitrogen, oxygen, and all of the halogens. So fluorine, chlorine, iodine, bromine, all of those come in diatomics. Or if you remember, I don't know if you remember Brinkelhoff. Has anybody ever taught you that?
No.
Okay, so let me do that. That's Brinkelhoff, Brinklhof. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Brinkelhoff. Those are all your diatomics. Okay.
Okay, thank you.
Okay.
Is what you said during the combustions, how you added the 3 oxygens and the 4 oxygens on the product side to find out what you need on the yield reactant side. Does that work for like all of them?
It does absolutely work for all of them. I'll be honest. When I look at this molecule, and this honestly gets to be when you do enough of these, you look at it right away. I look at ethane, and I know that when one of my products is water, so it's going to be H2. And so I look at that and I know that I'm going to have an odd number of water molecules. If I have an odd number of water molecules, that's automatically going to give me an odd number of oxygens on this side. And so I know when I look at this, I automatically know that I'm going to have to multiply that by 2. But truthfully, that comes from, I've been doing this for a lot of years. I've been doing this for 20 years. So I know that. It's probably easier for you to just go through the exercise of doing it and just counting the oxygens on this side. And when you have an odd number, you end up with a fraction on the reactant side, which you just have to clear by multiplying by 2. But it will happen. It will happen a lot with the diatomics. There are other elements as well. We just saw one. You saw one here in S8. We're going to do another one in a practice problem that you'll see, which is phosphorus, which comes as P4. So sometimes you'll see it with others, but you definitely see it with the diatomics. Okay, so when you're writing these equations, you also have to include the state. And the reason you have to include the state is because there will be times when the only evidence of a reaction that you see is a change in state. You could write a chemical reaction for melting of ice. The only difference between the reactant side and the product side in writing that reaction is the state of the water. It's a solid on one side, it's a liquid on the other. So knowing the state and recording the state is extremely important. Another reason why states are important is that sometimes the state is going to govern how something reacts. So you need to put the state in. And so here are some common sense and some tricks that you can use to figure out what the state is. The first is that the question may actually tell you. You're going to have to read the question. You're going to be given sentences and asked to convert those into chemical reactions. And very often you'll be told what the state is. You can get the information from the statement. But you can also use common sense. You should know some things. You should know that ammonia is a gas, that methane is a gas. C6H6, that's benzene. This is benzene. Benzene is a liquid. Anything with nitrogen and oxygen, doesn't matter what the subscripts are, those are gases. C6H12O6, that's sugar. That's a monosaccharide. That's sugar, and that's a solid. There are some things that normally you would expect to be in one state, but are indicated to be in another. For example, carbon dioxide is often, it was generally a gas, but if the problem says dry ice, then you're talking about carbon dioxide as a solid. If you're told ice is the reactant or the product, then you're talking about water as a solid. If it says steam, then you know that you're talking about water as a gas. Otherwise, water would be assumed to be a liquid. Another way you can figure out the state would be, if it's an element, look at the periodic table. There are very few that at room temperature are gases. Hydrogen, nitrogen, oxygen, and fluorine and chlorine are gases at room temperature, as well as the noble gases. There are only two elements that are liquids at room temperature, mercury and bromine. So if bromine is a reactant, it's going to be a liquid. When you're looking at compounds, if it's ionic, then it's going to be a solid. The exception is if it's listed as aqueous. So let me just say that the states that we have as possible are solid, liquid, gas, and aqueous. Aqueous means dissolved in water. So if it's an ionic solid, it's going to be listed as S. If it is listed as a solution, it would be aqueous. It's going to be dissolved in water. And we're going to talk about solubility rules in a little bit. Molecular compounds, it really depends upon the size of the molecule. If there are 1 to 6 atoms in it, it's a gas. If there are 6 to about 15 atoms in it, that's a liquid, and anything greater than 15 atoms is probably a solid. When we talked about naming, we talked about acids, anything where H is listed first. Those are in aqueous solutions. So if it says aqueous, those are an acid. And if you're told hydrochloric acid, you know that the state is aqueous. If the sentence says hydrogen chloride reacts, then you know that it's a gas and the state is a gas. So you can get your clues very often from the statement, but that would be named as a molecule. So you'll need to use your common sense on some of those. So we're going to practice writing a couple of these, and I'm going to show you what I mean. I have these written down, and we're going to do these separately. So the first one there is, come down a little bit, there we go. Sodium oxide must be kept away from water as the two combine to form a corrosive solution. So we have some indications here. Sodium oxide, this is an ionic compound. So this is likely to be a solid. And so we're going to list that as a solid, and it must be kept away from water. Notice it doesn't say it has to be kept away from steam. It says it must be kept away from water. So water we're going to put in as a liquid. So let's put our reactants in. We have Na2O, sodium oxide, solid, plus water as a liquid. You'll see many different ways of indicating the arrow that goes to the products. In this case, combine to form, that is our arrow. Yields is another way we can indicate the arrow. So combine to form, and it forms a corrosive solution. Solution is going to mean it's going to be aqueous. And the product is sodium hydroxide. So sodium hydroxide, and this is aqueous. Okay, now all we have to do is balance it. Okay, we have 2 sodiums on the reactant side, so we need to have 2 sodiums on the product side. We have 2 oxygens and 2 hydrogens on the reactant side. And by putting this 2 in front, I have 2 oxygens and 2 hydrogens on the product side. So that is balanced. Okay, that's our complete equation. Okay, so let's look at our second one. And this is the one that I told you we were going to look at. White phosphorus is a dangerous allotrope. Does everybody know what an allotrope is? Yes? No? Raise your hand if you know what an allotrope is.
I don't know what an allotrope is.
Thank you, Haley. Okay.
Welcome.
An allotrope means a form of something. They're different forms of something that are comprised of the same element. So for example, diamond and graphite are both allotropes of carbon. They both are pure carbon. They're just linked together in a different way. Buckminster fullerenes is another allotrope of carbon. So ozone and oxygen would be 2 different allotropes. Oxygen is O2, ozone is O3, both comprised of oxygen, but linked in a different way. So those are 2 different allotropes. So white phosphorus is a dangerous allotrope of phosphorus that is pyrophoric. I bet you all know what pyrophoric is, right?
Does that mean like flammable?
Highly flammable. As soon as it comes in contact with oxygen, it means that it can self-immolate, if you will. It will light itself on fire as soon as it comes in contact with oxygen. So pyrophoric, on contact with oxygen, the reaction yields diphosphorus pentoxide, which smells of garlic. So that's our sentence. White phosphorus is P4, and it is a solid. It's a waxy solid, okay, P4, and it reacts with oxygen. So we're going to put in our O2 gas. And in this case, the reaction yields, there is my arrow, the reaction yields diphosphorus pentoxide. Now, I'm going to tell you something tricky about this one, but we will write this as named, diphosphorus pentoxide. Anybody want to tell me the formula for that? Based on our naming.
Is it P2O5?
P2O5, yes, P2O5. Now, that would be based on the name diphosphorus pentoxide, and that is absolutely acceptable. I will accept that completely. However, I will tell you that in this reaction, it actually becomes P4O10. And believe it or not, in just a contrarian way, chemists will call P4O10, they will call that diphosphorus pentoxide as well, because it's named for its empirical formula, not for its molecular formula. Just as an aside, that's the way this is named, and I will accept both of these. This is what most experienced chemists will write, but this is perfectly acceptable. And based on its name, that's what I would have put when I was a beginning chemist as well. So when I balance it, this one is actually a little bit easier to balance, but I will point out to you that regardless of which formula you use, the balancing would be exactly the same. If I have 4 phosphorus on this side, I need 2 P2O5 molecules to balance that. That's going to give me 10 oxygens. And so I'm going to need 5 oxygen molecules because that would give me 10 oxygens. Okay. It would be 1 to 5 to give me P4O10 as well. Okay, so that's, it balances essentially the same way. Okay, so I would like you all, I'm going to put you in breakout rooms, and I would like you all to practice. The first discussion that you'll see is giving you some practice looking at some sentences and converting those sentences. This, by the way, is what we would consider an English sentence. This is what we consider a chemical sentence. So I'm going to ask you to look at a couple of those and try to create chemical sentences to go with those statements. So I'm going to open the rooms and you have about 10 minutes to work on those. Okay, so.
I'm doing good so far.
Okay, everybody understands what's meant by byproduct on the first one?
Yeah, I am, at least.
Okay. The only other thing I will tell you is that the one question that came up in other rooms, yes, you do have to know what methane is. That's a very common substance. Methane, ammonia, water are common substances that you should know the formula of. Everything else should be named according to the naming schemes that you've learned. If it's something unusual like the aluminum carbide, I will give you the formula. Otherwise, you should know them. Okay?
Okay, sounds good. Thanks.
First one, would you mind if I just confirm if it's right?
Sure.
Okay, so I got Al4C3 plus 12H2O. Then the reaction sign. 3CH4 plus 4Al, then parentheses OH3.
And I have something different.
I'm sorry, I have to see if we do this, that's 3, it's Al4C3
Yeah,
and H2O. Okay, so 4 plus 12, I believe. 6.
Do you mind showing us what, like, how you get it? Because I'm still like confused.
Yeah, I got lost on that one.
Like the more I try to balance them out, the more it's getting more and more numbers.
Okay,
So like,
so let me switch my camera.
Can you also go over how you know if it's a solid or liquid or aqueous?
I don't remember what that, did it, I think it told you, wasn't it? Didn't it tell you that aluminum carbide was it's AL. I'm sorry,
It was right.
give me the formula for aluminum carbide again.
AL4, AL4,
C3?
C3
Okay,
plus H2O.
plus H2O.
And
This is going to be a solid, by the way, because
Yeah.
it's basically ionic.
it
And this
gives,
would be liquid.
it
It should
gives,
give it to you. It should give it to you.
yeah, CH4 plus OH.
This is a gas plus,
ALOH3.
ALOH, yeah, ALOH.
and that's also a solid because that's an ionic compound. Okay, so I would, let's see, if I would normally say 3, okay, so I'm going to have 3 methanes, and I have 4, so I would put a 4 in front of the aluminum hydroxide. And now let's see how that balances. We've left the oxygen and the hydrogen for the end. So we have 3 times 4, so we have 12 hydrogens here, and we have 3 times 4, 12 hydrogens there. Am I right? Because there's 3 hydroxides, so 3 H's plus 4. You also have 3 O, and you have 12 oxygens. Okay, so that ratio is 2 to 1, so you have 12 water.
Yeah. That's what I got.
Okay,
I'm sorry. How do you get like 12 oxygen?
because you have 3 in each aluminum hydroxide formula, and you have 4 of those formulas, so 4 times 3
okay.
is 12. Okay,
Thank you. Yeah.
all right. Yeah, sometimes if you make a mistake counting somewhere, you can end up going down a garden path that takes forever to balance it. Okay, understood, but
I had a quick question.
yeah.
What if we mess up for some reason the formula, but we balance it correctly?
I will tell you that it is highly unusual if the formula is messed up that you can get it balanced correctly.
Okay.
Occasionally it can happen. In general practice, I try to give you 2 points for writing the correct reactants, 2 points for writing the correct products, 1 point for balancing, and 1 point for the right states. So that formula would give you 6 points. In general, is the way that I would normally do it. And I can tell you that it's highly unusual for you to be able to balance an equation if you get the formula wrong. So if I had aluminum hydroxide, if I had a 2 here instead of a 3, I would have real trouble balancing that equation because I'm getting some of my hydrogens from the methane. So it's just, it would not work very well at all. Okay, so let's go back. Okay, I'm sorry, I do want to change my camera here. Oops. Clicking the wrong thing here. There I am. Okay, now I want to go back to sharing my screen and we'll move on. We only have a few more slides that we're going to do today.
Professor?
Yes.
There was a way I was taught in high school to do it where you had to draw like a table, then you write out the numbers, then the moment you like balance the other side, you have to change the number of the other side so it makes it easier. But sometimes it takes longer.
Yes,
So
it
how
can
much-
take longer.
Yeah. So how much time are we gonna be giving on the exam to like balance equations?
That's a good question. That's a good question. And I don't really know. I guess it depends upon how complex the equations are. I mean, many of them end up 1 to 2 to 1 to 2. I mean, they're very simple. So those you would need a lot less time on.
Okay.
So I usually allow several minutes for each, and it depends upon what kind of a formula you're being asked to do as well.
All right.
What we were just doing was molecular equations. All of the formulas that we've used have been formulas for compounds, and that is called a molecular equation. Here we have a reaction between aqueous calcium chloride and aqueous silver nitrate. And these are ionic compounds. All of these compounds, both in the reactant side and on the product side, are ionic. And you'll note that they are aqueous. If they are aqueous, ionic compounds, when they dissolve in water, break up into ions. You don't have isolated calcium chloride units floating around in solution. What you have in solution is calcium ions surrounded by water molecules and chloride ions surrounded by water molecules, all floating independent in the solution. So your calcium chloride becomes calcium 2+ aqueous and chloride aqueous. Notice that this 2 in the Cl2 becomes a coefficient. That's because Cl2 2- doesn't exist. Chloride ions are Cl-, but we have 2 of them to balance each calcium ion. In our formula for silver nitrate, they become silver ions and nitrate ions. In this case, we have 2s in front of them because that's what we got from the balanced molecular formula. Calcium nitrate, the product here, is also aqueous. So those calcium ions are still floating around in aqueous solution, and our nitrate ions are still floating around in aqueous solution. Notice that the other product, silver chloride, is a solid. This is not separated into ions. It has to be written as a solid. So we could, if we wanted to represent this equation and give a better picture, if we wanted to put on our molecular glasses and actually see what's going on in this solution, we would write this as an ionic formula. We would write these reactants and products in the state that they actually exist. So calcium chloride aqueous becomes Ca2+ aqueous plus 2Cl- aqueous. Our silver nitrates here become 2Ag+ aqueous and 2-nitrate ion aqueous. On the product side, our calcium nitrate aqueous becomes Ca2+ aqueous and 2-nitrate ion aqueous, plus our silver chloride, which is a solid. That is written as a solid. But you'll notice that there are some species that haven't really changed. Calcium ion aqueous exists on both sides. It hasn't actually participated in any way in the reaction. The nitrate ions exist on both sides, unchanged. They haven't participated in the reaction. So we can actually cross those out on both sides of the equation because they really are just sitting there. We call those spectator ions. They haven't actually participated in the reaction. They were there present in the solution before the reaction. They are there present in the solution after the reaction. The only species that actually took part in the reaction are the chloride ions and the silver ions forming AgCl. And that is called a net ionic equation. I will point out that in this case, because of the overall balanced equation, we had two chloride ions, two silver ions forming two silver chloride. A true balanced equation is lowest whole number ratios. So those twos would disappear technically in the net ionic equation. The net ionic equation is simply the reaction between the silver ion and the chloride ion forming silver chloride. So I'm going to practice doing this one. Let me stop sharing my screen, and I'm going to switch cameras here. So here is my reaction, the reaction that I'm going to do as a sample. This is a reaction between aqueous potassium chromate and barium hydroxide. Aqueous forming KOH aqueous and barium chromate. So the first thing I might do is balance this. And I see that I have two potassium ions and two hydroxide ions on this side. So I need a 2 in front of the KOH. And that's all that's necessary to balance this. This one's not very difficult. But I want to represent this as it's really existing in solution. So I have 2K plus aqueous plus chromate plus barium ion, Ba2 plus aqueous, plus 2 hydroxides. Again, remember that this 2 becomes a coefficient. I have 2 hydroxide ions that are aqueous. And on the product side, I have 2 potassium ions aqueous plus 2 hydroxide ions aqueous plus barium chromate solid. And now I can look to see what hasn't changed. Well, my potassium ions are the same on both sides. My hydroxide ions are the same on both sides. So my net ionic equation is chromate, excuse me, I'm calling this chromate. It's not chromate, it's oxalate. Please forgive me. It's oxalate aqueous plus barium aqueous forming barium oxalate solid. And that's the net ionic equation.
How come the potassium gets a plus?
I'm sorry?
How come the potassium gets a plus up top? Like it's not.
It's an ionic compound. And so this represents an ionic compound. And when ionic compounds break up into solution, they break up into the component ions, potassium ion and oxalate ions.
Okay.
And barium ions and hydroxide ions. So you know the charge based on the counter ion. Barium is 2 plus because there are 2 hydroxides to balance it.
I see what you're saying.
Do we
Okay.
just have to memorize which ions exist?
No, you have to recognize it as an ionic compound. And remember, when we did naming, we knew it was an ionic compound if it was made from a metal and a nonmetal.
Ah.
Okay.
Okay.
So these are metals and nonmetals, then they're ionic compounds.
Thank
Okay?
you.
If it's made of all nonmetals, it's molecular. Okay, I believe that there is another discussion for you to do. I'm going to open up the rooms again, and I'm going to let you guys do a practice on writing a molecular formula, balancing it, and writing net ionic formulas.
Professor,
Yes.
when you were working out the net balancing, I
Mhm.
wanted to ask, how do you know right off the bat which one has a negative or positive?
Which one has a negative what?
Which one has the positive or negative charge?
Metals are always positive.
Okay,
And whatever's written first, the ion that's written first will always be the metal, and it is always positive.
okay,
And the counter ion will be negative.
all right, thank you.
Plus and sulfate.
Okay, thank you.
Okay.
Hi, Professor. For
Yes.
CO2, so C is like -2, and then like it has the negative charge of 2, right?
I'm sorry, what's the compound? What's the compound?
CO2.
CO2 is not an ion. That's a molecule.
Okay.
It's not an ion.
So we just leave it there.
Yep. It's a gas. Carbon dioxide, it's a gas. Carbon dioxide and water are products, and they are molecular products. They are not ionic products. You know that they're molecular because they are all non-metals.
Mm.
The only ones that are ionic are the ones that start with a metal.
Okay.
Okay.
Can I read you what I have and see if I'm right?
You really want to what?
Can I read you what I have and see if I'm correct?
Okay.
So it's Pb2 plus NO3 minus plus H2 plus SO4 minus.
No, it's not H2 plus. It's 2H plus. There is no such species as an H2 plus.
Okay, so it's 2.
2H plus plus SO4 2 minus.
Okay, where'd you get the 2 minus then?
Sulfate is SO4 2 minus. That's a
Oh.
polyatomic ion, and you have to know that.
Okay.
Okay.
Can you go
know,
over it real quick? I'm
Huh?
sorry. Can you go over it real quick for the first one?
What's the first one?
Discussion?
I will in a minute, but I want to, let me finish there's 2 slides I want to do because the subject
Okay.
came up. The subject came up, and then I'm happy to go over any ones that you had questions on. One of the questions that came up is somebody said, well, everything here is soluble. Knowing whether a compound is soluble or not is critical. As I said, some ionic compounds, many ionic compounds are actually soluble in water. Some of them are not particularly soluble, not very soluble at all. And you'll find out in second semester that right now we're gonna call them insoluble, but in second semester, you'll find out that to a very minor degree, some of them will dissolve a little tiny bit, but we're going to consider them insoluble for now. So the question is, how do you know whether an ionic compound is actually soluble in water? And in order to know that, you have to know the solubility rules. And that's basically what I'm showing you here. And the solubility rules, unfortunately, it's not always clear cut. But you'll see that they break out into 2 different categories. The top are those that are soluble, and the bottom are those that are insoluble. So we have rules for both. The first rule for soluble compounds is any compound containing a group 1 metal, lithium, sodium, potassium, rubidium, cesium, group 1 metals, salts, are always soluble, and also anything containing ammonia. So ammonium, whatever, ammonium sulfide, ammonium chloride, those are always soluble. There are no exceptions to that. All group 1 metal salts and ammonium salts are soluble. The second rule is regarding the halide ions, chloride, bromide, and iodide. Those salts are considered soluble, but there are some exceptions. The chloride, bromide, and iodide salts of silver, mercury 1, and lead 2 are insoluble. The halide ion salts containing F minus, those are going to be soluble. The exceptions are anything for group 2 metal cations plus lead and iron 3 plus. So iron fluoride would be insoluble. Most fluoride salts are soluble. Iron 3 fluoride would not be. Lead 2 fluoride would not be. And anything in the group 2 metal cations, calcium, magnesium, those fluorides would also not be soluble. Acetate, bicarbonate, nitrate, and chlorate ions are always soluble. No exceptions on those. No exceptions. Sulfate ion, and this came up in one of your examples, sulfate ion salts are soluble. Sulfate salts are soluble with some exceptions. Silver, barium, calcium, mercury 1, lead, and strontium. Those salts are insoluble. So those are the rules governing the soluble compounds. What about insoluble compounds? Salts containing carbonate, chromate, and phosphate are insoluble. The exception to that is any compound that's made with a group 1 metal or ammonium ion. That means that this rule up here supersedes this rule. Anything made with combining a group 1 metal or an ammonium ion with these salts, carbonate, chromate, phosphate, and sulfide, those will be soluble. Anything else, any other metal cation with those anions is insoluble. Hydroxide salts are insoluble. Again, the exception is group 1 metal cations, but also barium hydroxide. Barium hydroxide is soluble. So that's another exception. So I will give you these solubility rules. The trick for you is being able to read these and being able to use them when you're trying to figure out the solubility and what, if anything, would be a solid product when I mix aqueous solutions.
So
yes.
Does that mean when we have, like, are we using those rules to determine what to cross out and what to not cross out?
Yes, you're going to use those rules to determine what is soluble and what isn't. So you would look, basically, we're going to talk about different types of reactions. Basically, if you look at those reactions, you see that when you mix them together, let me go to this next one for a second. When I mix aqueous solutions, notice it says solutions. When it says solutions, that means it's aqueous. So lead 2 nitrate, this is aqueous, and potassium iodide are aqueous. So I know what the states are for those two. When it says solutions, they're aqueous. Now, notice that this is going to form K plus ion in solution and I minus ion in solution, lead 2 plus ion in solution, and nitrate ion in solution. Those are really what I have. Now, when I have those ions floating around together in solution, the question is, will I form an insoluble precipitate? If these two come together, if they were to come together, I'm really just forming my reactant. So that's not going to change anything. If these two come together, it's just forming a reactant. We already see that those are soluble. So those are not going to form any kind of insoluble precipitate. The only way you form a precipitate is if the anion from this first compound goes to the cation of the second compound, or the cation of the first compound joins with the anion of the second compound. It's called a double displacement reaction because my cations and anions are switching partners. They're just going with the counter ion from the other compound. And so I'm looking at lead iodide and I'm looking at potassium nitrate to see if those form insoluble compounds. And that's where I have to use the solubility rules. And I see that nitrate compounds are always soluble, no exceptions. But for the halide ion iodide, they are generally soluble, but I have exceptions, including lead 2+. So that tells me that this is my solid and this is aqueous. And now all I have to do is balance it. So I have 2 iodides here, so I have to put a 2 there. That gives me 2 potassiums, so I need a 2 there. That gives me 2 nitrates, but I have 2 nitrates, so 1, 1, and it's balanced. So this bright yellow precipitate that you see up here, that bright yellow precipitate is lead iodide. So that's basically how you would apply the solubility rules. And we're going to talk more about different reaction types, but this is called a double displacement reaction. Okay.
Okay, so we cross them out if they're soluble.
If they're soluble, if they're still in solution, we call those spectator ions. They really just came to the party, but they didn't do anything. They just stayed floating in solution. And those are not taking part in any way in the reaction. So you can cross those out.
Okay.
They are used essentially as a vehicle to get the other ion in solution, right? So nitrate is a way of getting lead ion in solution so that it can react with something else. Because lead often forms insoluble precipitates. So how do I get a counter ion? How do I get lead ion in solution? I use a nitrate salt because nitrates are always soluble. If I have an insoluble, like a hydroxide, most hydroxide salts are insoluble. How do I get hydroxide into solution? I'll use a group 1 metal like sodium or potassium. That allows me to get the hydroxide ion into solution so that it is there to react with something else.
13 O2. We're going to have 8 CO2 molecules and 10 water molecules.
Somebody's balancing.
Make sure.
John.
Oh, sorry.
That's okay. It's okay. Any other questions? Any other questions or problems? These are called precipitation reactions, and we're going to use net ionic reactions for other types of reactions, but they're very common for precipitation reactions like these. Okay?
Professor?
Yes.
Well, do you have like a couple minutes after class?
I
you
sure
go
do.
over the discussion?
Yeah, I can go over the discussion. Let me see if I have it on my screen. I do not. Well, yes, I do. I can have it. I can pull it up. Okay. This is the second discussion, molecular and net ionic equations.
Yes.
Okay. Let me. I can share my screen again. Okay, so this is is it the second one that's giving you problems?
I confused both of them. So can you just go over both of them?
Okay. The first thing I will point out is that if you C aqueous, like you do for these first two compounds or this last compound, that means that those ions are in solution. What you haven't seen yet is something like this HNO3, which is an acid. HNO3 is an acid. It's not considered ionic, but it's a strong acid, and strong acids break up into solution as H plus ions and nitrate ions. Okay, so the nitrate from the left side and the hydrogen ion from the left side are still, these are going to be aqueous on this side. This is also H plus SO4. These are not balanced, obviously. I need a 2 in front of that. Lead is Pb2 plus and nitrate is NO3 minus. So this is what's on this side. These are the aqueous ions on this side. And on the other side, you still have the H plus. So the H plus is going to end up canceling and the nitrate is going to end up canceling. And the lead sulfate forms your solid precipitate. Now you have to balance it. It's often easier to balance it in molecular form first. So we have 2 nitrates here, so we'd have to put a 2 in front of the nitric acid. That's going to give us 2 hydrogens. We have 2 hydrogens, so that's balanced. It's 1, 1, 1, and 2. Now on this side, notice that this goes in as a solid. So it is not broken into ions. It's simply written as calcium carbonate. But this is H plus, aqueous.
So you can't break that one out.
This one,
You have to say
this
the
is
same.
aqueous. The
Okay.
acid does break up. If it does break up. Strong acids, and we'll be doing more about strong acids later, but still in this chapter, but we're going to get to acid-base reactions. Strong acids do break up, just like ionic compounds. They break up into component parts. So it's calcium carbonate plus hydrogen ion plus sulfate ion. This is aqueous, forming calcium sulfate solid, carbon dioxide gas, and water as a liquid. Now, as I said, you're going to want to balance that first, but I want to point out to you that you have nothing aqueous on this side, do you?
No.
There's nothing aqueous on this side, which means that your hydrogen ion has changed form. It's gone from H plus to water. Sulfate has gone from aqueous to a solid calcium sulfate. Carbon from here in your solid has gone to a gas in carbon dioxide. This net ionic equation is essentially as I've written it, except that it's not balanced. Calcium carbonate solid plus 2H plus aqueous plus SO4 2 minus aqueous forms calcium sulfate plus carbon dioxide plus water.
So Professor, for these molecular net ionic equations, do we just have to balance them, or do we have to break up like the acids and everything?
It depends upon the way the question is asked, to be perfectly honest. It depends on the way the question is asked. If I've asked you to balance it, just balance it. If I ask you to write a molecular and a net ionic equation, you have to break everything up that dissolves in water through ionization. You have to represent them as ions. The idea of an ionic equation is to represent the species in the form that they're in when they react. We're going to talk more. Don't worry too much about it now. We're going to talk more in another day or two about acids. I think it's going to be next class period. We will talk more about acids, and I will identify which compounds are strong acids. Strong acids break up in solution into ions. Weak acids do not. It's one of the few things I'm going to ask you to memorize in chemistry. I will ask you to memorize the strong acids. There aren't very many of them. Nitric acid, perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. So all the hydrohalic acids, with the exception of HF. HF is weak, but HCl, HBr, HI are all strong acids. Nitric acid is strong. Sulfuric is a strong acid, technically only for the first proton. The second proton is considered weak. So we'll talk more about that when we talk about acids, but those are your strong acids. You have to memorize those. And perchloric acid. There are six strong acids. Everything else is weak. And weak acids do not break up into ions. They go into solution as molecules. So HF does not break into ions. It's represented in solution as HF aqueous. Hydrochloric acid is strong, and it will be represented in solution as H+ ion plus chloride ion, aqueous. Okay, we'll talk more about that when we talk about acids.
Professor?
Yes.
Last question. So breaking them down into like net ions doesn't affect the equation. You just want us to show you, right?
Yes, it does not affect the equation, and that's why it's
Okay.
often easier to balance it as a molecular formula.
Yeah.
The only thing that does is represent the species as they exist in solution.
Okay, makes sense. All right.
Okay.
Thank you.
Okay. All right. That's it for today, guys. I'll see some of you for lab tomorrow.
Thank you.
All right. Have a
Okay.
nice day.
You
Take care.
too.
Thank you, Professor.